let's start with a problem that is about pulling a weight up using a rope. I'm going to look at number 14 here, though I am going to modify the problem a little bit. 1,000-pound weight. The first thing you should think of when you see the word weight here in this context is to remember that weight is a force. So if it's British non-SI units, it's going to be in pounds. That already is a force. If it's in SI units, it would be given as a mass. You have to multiply by 9.8 to convert it to a weight. Mass and weight are different. But here we're using British units, 1,000-pound weights being lifted to a height of 10 feet. Here's where I'm going to change it. I'm going to, instead of lifting it to a height of 10 feet, I'm going to lift it all the way to the top of the roof, which is 30 feet off the ground. It's lifted by a rope that weighs 4 pounds per foot and is being pulled by construction workers standing on a roof 30 feet off the ground. Find the work done to lift the weight. Yeah, I'm changing it. I'm going to make it lifting the weight all the way up to the top of the roof. So this is section 8.5, number 14, modified. Sorry, that's blurry. Get better. Maybe if I take this away, it'll get better. There we go. So here's your building. Some workers standing up here, pulling on a rope attached to, say, a pulley here, pulling a weight up off the ground. Obviously, they're going to have to expend energy to pull this weight up off the ground. If you can figure out the total work done to pull it all the way to the top, 30 feet here, that's the same as the amount of energy they're going to expend. Although if it's more than one person, then they're going to be sharing the load. And this weight is heavy enough that it would have to be more than one person. The value of the weight, its weight amount, which is again a force, is 1,000 pounds. To figure out the work done to pull the weight itself up, you don't need to use calculus. You can just do the weight, which is a force, times the distance. 1,000 is the weight. Yeah, double check, it's 1,000 pounds. Times 30 feet, that would be 30,000 foot-pounds. But the problem can't possibly be that simple, right? It's in a calculus book and it's not the first few problems. It must be harder. How is it harder? What makes this harder than that? Go ahead. Yeah, the rope has weight. The rope weighs 4 pounds per foot. Okay, so then maybe we should just figure out the weight of the rope and multiply it by 30. Problem with that is that as you pull the weight up and the amount of rope that is hanging straight downwards gets smaller and smaller. When the rope comes over the pulley, then it can lay on the rooftop and it doesn't affect things. The amount of weight you're pulling gets smaller and smaller as you keep pulling upwards. So the force gets smaller and smaller. You can't just multiply the force times the distance. And another thing is the force, the distance changes depending on which little chunk of the rope that you're thinking about. And that's what we want to do. We want to imagine cutting this rope into little tiny chunks of, say, length delta y. Such a small chunk, well, if it is really small, the rope molecules, pretending there are rope molecules, travel approximately the same distance up to the top of the roof in that small chunk, but different small chunks travel different distances. And it's that fact that different small chunks travel different distances that means you need to do an integral. Though we will see this actually still can be done without an integral, but I want you to use an integral on your homework. For one thing, for your benefit, so you're practicing these skills, and for another thing, so for the graders' benefit, so they don't get confused by what you're doing. Okay, you don't want to confuse the graders, right? That's a fundamental thing about homework, is don't confuse the graders. Try to make things look as nice and simple as possible, so you get as much partial credit as possible. What's this distance here? Well, it would depend on my labeling. If I decided to make the positive y-axis go downward, which I could, then that distance would be y. If, as typical, I want to make the positive y-axis go upward, then I'd call this distance y, and therefore this distance would be 30 minus y. Let's do it in the typical way. So how should I set things up? How should I write my, first of all, my approximate work done for a small chunk? Well, okay, before we do that, we should figure out the weight itself. The work done on the weight itself ignoring the rope is just that weight, 1,000 pounds, which again is already a force, times the distance the weight has to go. The weight does start at ground level, so it's got to go 30 feet. So this is going to be 30,000 foot-pounds. Oops, 30,000 foot-pounds. It's where I think about the work done on the rope that I have to use calculus. Once I get an answer for the work done on the rope, then I just add the results to get the final answer. For the rope, first think about the small amount of work done, call it delta W, on the little chunk of the rope. It would be the weight of that little chunk times the distance it travels, 30 minus y. The weight of the little chunk, we need the density of the rope. We were given that. It's 4 pounds per foot. The weight density is 4 pounds per foot. Multiply that by that little length in feet, and you get the approximate weight of that little chunk. In fact, the weight density is constant, so it would actually be an exact equality. 4 pounds per foot times delta y feet. Okay, that's the exact weight, but I'm after the approximate work. This W stands for work, not weight. That's the weight. I could call it delta weight if I wanted to. The approximation comes from approximating the distance to be 30 minus y. And that's an approximation, partially because I haven't even specified exactly what y is. Is it the distance from the ground to the bottom of this little chunk, or the top, or somewhere in between? We don't bother specifying it because it doesn't matter in the end. We end up doing an integral that's the same either way. And this could then be written as 120 minus 4y times delta y. And this would be in joules. This is for the small chunk of rope. Then for the total, the entire rope, total work for rope. Conceptually, it is the sum of the small works, which is then going to be approximately a Riemann sum that looks like this. And as always, We let delta y go to 0. We pretend in our minds that the summation sign morphs into an integral sign and the delta y morphs into a dy, but the function here stays the same. 120 minus 4y dy, but we do need a definite integral. We're looking at the entire rope going up the entire way from 0 to 30. Y goes from 0 to 30. So these integrals typically do end up being fairly easy to do once you figure out what the integral is. This one's no exception. We get 3,600 is 120 times 30 minus 30 squared is 900 times 2 is 1,800. And then when you plug in 0, you get 0. In the end, we get 1,800 foot-pounds for the rope. That's not the final answer. Final answer now is what I get when I add the work for the weight and the work for the rope. The weight, it was 30,000 foot-pounds plus the rope is 1,800. So I get 31,800 foot-pounds. Question? Oh, yes, thank you. Foot-pounds. This actually can be done without calculus, even for the rope. How? Because what you could do is you could pretend all the mass of the rope is in the middle of the rope, 15 feet high and travels 15 feet. The weight of the entire rope would be 30 times 4, 120 pounds. If you pretend that entire weight was in the middle of the rope and traveled half the distance, 15 feet, multiply that by 15, you still get 1,800. You still get that number. So it really could be done without calculus, but use calculus anyway, partially to practice, partially not to confuse the grader. Okay, can I clarify anything else? Next problem. Turns out also can be done without calculus, but I want to do it with calculus anyway. However, not all of these kinds of problems can be done without calculus. I'm thinking of problem number 18 here. Oh, before we do that, I should mention what to do if we were using SI units here. If, for example, instead of a weight density, this was a mass density of, say, 4 kilograms per meter, and this weight was really a mass of, say, 1,000 kilograms, you'd have to convert those to weights first by multiplying by 9.8. That would, so 1,000 kilograms would correspond to 9,800 newtons. And 4 kilograms per meter would correspond to 4 times 9.8 is 39.2 newtons per meter as a weight density. And that has the effect of multiplying your answer by 9.8, and the answer would be in joules then. Okay, back to the water pumping problem. So it's going to turn out in this problem, we will use calculus to do it, but it can be done without calculus. However, not all problems like this can be done without calculus. There's an example in the book, it's example 5, where calculus must be used. Because in this example, the tank, the water tank, or an oil tank in this case actually, is shaped like a cone. And the cross-sectional area is not constant. And because of that, calculus has to be used. In the problem we're about to do, the tank is a right circular cylinder, a can shape. So the cross-sectional area is constant. And that's why calculus can be avoided. But let's get practice with calculus anyway. So yeah, what is the situation? Right circular cylinder, can shape, height of 20 feet, radius of 6 feet. The tank is half full of water. Find the work required to pump all of it over the top rim. So we're pumping water out of the tank. And once again, work is it's in energy units. So this does correspond to the amount of energy the pump is exerting to pump the water out. So make a drawing. Here's your tank. It's a right circular cylinder, a can shape. 20 feet tall, 6 feet in radius. And it starts half full of water, which I will make blue. And this affords me the opportunity of telling you a little story. When I was young, especially 10, 11, 12 years old, my goal in life was to be a cartoonist. And maybe I've told you this, I made like hundreds of cartoons actually, though my sad story, my dog eventually threw up on a lot of them and I had to throw them away. So I took some drawing classes in school and I was pretty good at drawing. Okay, I guess. Not the greatest, as you can see, but okay. I took a painting class. I wasn't so good at painting compared to drawing, at least. And my teacher didn't really like me, it seemed, because he kind of ridiculed my paintings. And in particular, I would make paintings of outdoor scenes with lakes and like trees in the background. And there was one in particular that I made where I also tried to paint a fisherman in a boat and a fish, and the fisherman was trying to catch the fish as it was jumping out of the lake. It wasn't the greatest painting. And anyway, I tended to make my water pretty dark blue, as often is the case when you look at water on the lake, because of not only the sky being blue, but also just what's under the water. But it was too blue for him, or maybe it was too bold of a blue or something. I don't remember. And one day he came over and he was looking at my painting. He's like, "Kenny, what color's water?" And I'm looking up at him. I'm like, is this a trick question? I didn't say anything. It's like, louder, "Kenny, what color's water?" And by now, everybody in the class is looking at me. And I still don't say anything. And I think he said it one more time. "Come on, Kenny, what color's water?" I'm like, blue? And he's like, "No, water's clear." And everybody laughed. Like, "I thought you wanted me to say a color. We always use blue." Anyway, so that discouraged me from sticking with painting. But just a few years ago, I'm serious, just a few years ago, I ran across an article that said, yeah, water seems mostly clear, but actually, if you scientifically analyze it, there is a slight blue tint to it, even when it's not just reflecting the sky. I'm like, yes, I was right. I think my teacher is probably not alive anymore, so I can't go back and find him. There we go. Yeah, maybe that's why I went into math, because my painting teacher didn't like me. And everybody laughed as if they knew he was going to say clear. Anyway, okay. Pumping the water out. So here's your pump up here. I can't draw a pump. Okay, let's just draw the hose. Here's a hose going into the water, pumping the water out. And again, the goal is to figure out the Total work done to pump all the water out. Sounds kind of scary. Okay. What we're about to do is going to seem very hand wavy. Fishy, you might even say. We're going to pretend that all the water molecules in any given thin slice of water travel the same vertical distance against gravity as they're being pumped out of the tank. Now, if you think too literally about what is literally going on, you know, water's like a gas. The molecules are going all over the place. I mean, they're closer together. They're maybe more interaction with each other. They're flying all over the place inside this tank, sometimes up, sometimes down, sometimes sideways, even as they're being sucked out. And you know, where is the bottom of this hose anyway? Is it at the top of the water line or is it at the bottom of the tank? If you want to leave it there to suck all the water out, you'd probably put it at the bottom of the tank. So it's got to suck the water molecules down first before they go back up. Well, they go all over the place. You know, they bounce all over each other, and they sometimes are going up randomly. And if they go down, then wouldn't they have to travel a further distance up? It's kind of confusing if you think about it too literally. But it turns out, for reasons I don't completely understand, I think I asked a physics teacher about this once, and I think he wasn't sure either, that you can assume that they just go up the same distance in any thin layer. And it gives you the right answer. I mean, you'd have to experimentally verify that, I imagine, but evidently it does give the right answer. Go ahead.
Well, I know from Gen Physics 1, I thought the answer to that was if you move something up and back down to the same location, it didn't move, so there's no work done.
Well, it did move, but you're right, there's no work done. There's no net work.
So if it goes down and back up, the work's happening again.
Yeah, I guess so. That's as good of an explanation as I can imagine, but I'm not quite sure. Let's say the width of this is delta y. And what vertical upward distance do these things have to travel? They have to travel 20 minus y, where this is y. So once again, the work done on the thin slice is approximately its weight, that's a force, times that distance, 20 minus y. So we got to figure out the weight. I could call it delta weight if I like. I'll leave just a plain W for work. Delta weight, which you could call delta F because it's a force if you like. Is going to be the weight density of water times the volume of the thin slice weight density of water times the volume of the thin slice, delta V. The weight density of water is in the book. You can look it up. Its mass density in SI units is 1,000 kilograms per cubic meter. Its weight density in British units is 62.4 pounds per cubic foot. In fact, I wonder, is that the fact that the mass density of water comes out to be such a nice number, is that the reason kilograms and meters have are the way they are? Maybe. So that number comes out so nicely. But in British units, it's not a nice number, 62.4 pounds per cubic foot, but that's a weight density, not a mass density. Gravity is already taken into account there. 62.4. Delta V is going to be the cross-sectional area times delta Y. Cross-sectional area is constant. It doesn't depend on Y. It's pi times 6 squared. Six squared 36. 36 times 62.4. 2,246.4 pi, don't forget your pi, times delta Y. And that would be in pounds. So the small amount of work done for the thin slice, this is an approximation because it's an approximate distance, is the force times the approximate distance, which is 20 minus y. So we get 2,246.4 pi times 20 minus y times delta y, and this is in foot-pounds. That's the approximate amount of work for the thin slice of water. Add those up for the total work for all the water. Calculate that by letting delta y go to 0 to get an integral. I won't write the summation out this time. Total work for all the water. You'll get an integral of this function here, 2,246.4 pi times 20 minus y dy. Y goes, careful, not 0 to 20, but 0 to 10, because the water is only up to 10 feet deep. If the water were deeper, like 15 feet deep, I go 0 to 15. Let's save a little time here, just have Mathematica do this. It's certainly something you can do fairly easily by hand. Zero to 10, 2246.4 times pi. You can do capital PI for pi. You can also do escape, P escape, or use a button on the palette. About 1.06 times 10 to the 6th foot-pounds. A little over 1 million foot-pounds. With SI units, would you just multiply everything by 9.8? Well, it depends on how the problem is phrased. If you were told the cylinder is 20 meters tall with a radius of 6 meters, got to be careful. No, you don't just multiply by 9.8. You do multiply by 9.8, but not right away. Or you don't just multiply this answer by 9.8 is what I'm trying to say. You need to use the mass density of water, which is not 62.4. It's 1,000. 1,000 kilograms per cubic meter. Multiply that by 9.8 to get 9,800 newtons per cubic meter. So effectively, instead of a 62.4, you'd have a 9,800. And the numerical value, the answer would be a lot larger, but it would be in joules. How much larger? 9,800 divided by 62.4, about 157 times larger. About that many joules if the original distance units were in meters. I think, I might be wrong. I think, is 1 joule less energy than 1 foot-pound? I think so. Although 1 meter is certainly longer than 1 foot. So, yeah, I mean, the units on the original problem are different and the units of the final answer are different as well. Could this have been done without a calculus? Yeah, it could have. What we could have done is pretend all the water is in the middle. How much water is there to start with? Pi times 6 squared times 10. 360 pi. That's the volume of the water to start with in cubic feet. Times 62.4. This is the weight of all the water to start with in pounds. If I multiply that by 15, pretending all the water's in the middle, halfway between 0 and 10, up 5 feet, so you got 15 feet left to go. I think we get the same answer. Yeah, that's the same answer, just not shown in scientific notation. Okay. But I might give you a cone problem. And even if I just give you a cylinder problem, do it with calculus anyway. Or I might give you a problem where the pool is shaped like a rectangle, or the tank is shaped like not a rectangle, but a box. The cross-sectional area would be a square or a rectangle. Pi would not be involved in that case.